So let's look at a graphical derivation of the Fourier transform. Now we've seen in the previous video that if we have this square wave here and it's got period t0 and the pulse width is tau, then we can represent this as the complex Fourier series which is shown below. So that's equivalent to our sinc function, and you can see that it's a purely real function. There is an imaginary axis there, but there is no phase component or imaginary component to this function here. And we've seen that its crossover point is given by 2 pi n upon tau, and the height there, Cn, is given by tau upon t0. And we know that the axis here as well, remember, it's a discrete axis, so it's multiples of a fundamental frequency omega naught, so that's axis is n omega naught. And we went through the derivation and we found out that the values of Cn, which are the heights of these phasors, is given by this sinc function here. So it's tau upon t0 times the sine of omega tau n upon 2 all upon omega naught tau n upon 2. So that's the sine x1x, which is the sinc function. So now we're going to look at a time delayed version of this, and we'll see how we can use that in order to derive the Fourier transform. So let's get a little intuitive idea of the time delay. If we were to take the original function which we've seen in the previous slide, which is f of t, and we delayed it by a certain factor tau, so that we get this new function f of t minus tau. So this is the same as the function in the previous slide, but it's just been moved along the axis to the right. Then in doing so, in the frequency domain, it's equivalent of adding linear phase on to all of the phasors. So the DC term would remain the same, but all of these other phasors in the positive n omega would rotate in one direction, and the negative n omega would rotate in the other direction, till eventually, whenever this function here has been moved along a full period and it now sits back on top of the original function, all of these phasors would have gone round the full 2 pi or 360 degrees, and they would be back to the original position. Now here's a little analytic proof of it. We know that we can represent f of t as the sum of all of these from our Fourier series. So if we were to take just one of them, and then if we were to look at the time delayed f of t minus tau, so we would have f of t minus tau would equal Cn e to the in omega naught t minus tau. So we split these two up, so we'll end up with a Cn e to the in omega naught t times e to the minus in omega naught tau. But this value here is just our original value of f of t. So we'd have original value f of t, and with this other term here, e to the in omega naught tau. So you can see up here that this e to the in omega naught tau, it doesn't change the magnitude here of Cn in any way. The only effect it has is to add the linear phase. So that's our little proof there that a time delay adds linear phase in the frequency domain. Now we're going to use this fact in order to derive the Fourier transform. So let's take this function f1 of t, and it's the square wave that we've started off with, and its period is t0. Then the complex Fourier series here is going to be given by the sinc function, which we've seen in the previous videos, and the components here have got height Cn. The component in the centre of that height of that is going to be tau upon t0. The crossover points are going to be given by 2 pi n tau upon t0. Now let's imagine we were to take this function and we were to shift it by half the period. So the new function here, f2 of t, would be f1 of t minus a half t0. So we've shifted it by half of the period, and it's shifted to the right. So it means that we've taken this function here and we've now produced this new function here. This point, this here, has been shifted over to here. Okay, and this one here has been shifted over to here, and this has been shifted obviously off of the diagram. Now we've seen then from the previous slide that if we shift them in time, it's equivalent to adding linear phase in the frequency domain. So if we were to look at these, the original DC term would remain the same. This term here, well, we've shifted it by half the period, so it's going to rotate by 180 degrees. Okay, so it's going to be steady facing up that direction, it's going to face down here. Now this term here is rotating at twice that fundamental frequency, so instead of rotating around the 180, it'll rotate around the 360, so it'll be back to its original starting position. And this one here would be rotating around the 360 plus 180, which is 540, so again it would be in the opposite direction. And each of these would change accordingly. Now the amplitude of them would be the same, so the height would be the same, but they would either be rotated by the 180 degrees or fixed in the original position. So in effect you're going to end up with two sinc functions here. You're going to have one that runs up like this, and you have another sinc function which runs this way. So there would be an envelope here generated by two sinc functions. Both of them are 180 degrees out of phase. So now if we were to take this square wave here and then add on this square wave here, we would get this function f of t, and the period here would be given by our value of t0. So in the frequency domain, if we were to add the terms up in the frequency domain, we would have this term here plus this term here, which would be in the same direction, but it would be twice the height, so the amplitude would be doubled. Now if we take the next term here, we would have this term plus this term, which would cancel out, so there would be nothing there, and the next one would have this term plus that term, which would be a term which would be double the height, and so on and so forth. And also in the negative n omega axis the same thing would happen. So we would end up with half the number of components, but each component would be twice the height. Now what we're actually interested in is looking at this in the opposite direction. So if we were to double the period, so from here up to this one here, the period is being doubled. Then we could say that we would double the number of components, but the height of the component would be half. Now if we were to take that as the limit as this value t0 tends off to infinity, then eventually we would end up with an infinite number of these components, but their height would be infinitely small. So in effect we would have nothing here, just a straight line along the n omega axis. So what use would that be? Well, we'll see what we can do with that in the next slide. So as we mentioned in the previous slide, if we were to double the period, then we would double the number of frequency components, but we would halve the amplitude of the frequency components. So I've thrown this out here. So if we were to say t0, the period there was to tend towards infinity, then this value of tau upon t0, which is the height there, cn, is obviously going to tend towards 0 as t0 tends to infinity. And that's just stated here. When t0 tends to infinity, tau upon t0 tends to 0. So in the limit we get an infinite number of components in the frequency domain of 0 height. So what we do is a little mathematical trick, and it's simply a scaling factor. So we noted that our tau upon t0 will tend towards 0 as t naught tends to infinity. But if we scale that by a factor of t naught, then we could say that t naught would divide by t naught, so it would all tend towards a limit tau. So our Cn t naught would tend towards this limit of tau. So the envelope, it wouldn't vanish, it would remain. So if we were to go ahead and do that, we know that as the period tends towards infinity, the number of frequency components tends towards infinity. So the value here of our Cn t naught, which is our frequency components, is going to tend towards a continuous function of frequency f of omega. So we can replace our n omega naught, that is the multiples of a fundamental frequency, with a continuous variable omega. Plus, as the period tends off to infinity, it means that we can now replace our values of our limits with plus and minus infinity. So let's go ahead and we'll put that into our forward transform, which we've seen previously. So our forward transform here, we're going from the time domain to the frequency domain. The values of our Cn was given by 1 upon t naught, the integral from 0 to t naught f of t to minus in omega naught t by dt. Now still remember that that what we're doing here is a dot product. So the dot product of the function f of t with the orthonormal basis e to the in omega naught t. But now we don't have Cn. We're replacing Cn with a scaled version. So the scaled version will be t naught Cn. So that's equivalent to multiplying this side by t naught. So the t naught will cancel out with the t naught. So that will disappear. Again, the limits were going from 0 to t naught. But the value of our period is tending off to infinity. So we could change that to minus infinity to plus infinity. Plus our n omega naught is going to tend towards a fixed frequency variable omega, a continuous variable omega. So adding all of this in, we're going to end up with our function f of I omega equals the integral from minus infinity to infinity over f of t e to the minus I omega t by dt. And this here is the forward transform. So we'll go and we'll do the same for the inverse transform. So now let's look at the inverse transform. We know that we can go from the frequency domain back to the time domain via this function here, which is their summation. So remember, this here is just us approximating a function f of t using a sum of cosines and sines, which are both all wrapped up into an exponential function here. But we've seen that we're now dealing with not the value Cn, we're dealing with the value of a Cn which has been scaled by a factor of t naught. So that means that in order for us to write this out in terms of our scaled version, in order to get back to the original value of Cn, we would have to divide that Cn by that factor of t naught. So this would be equivalent to 1 upon t naught times this function here. Now we know that we can write omega naught as 2 pi upon t naught, so it means that 1 upon t naught, which is what we have here, would be equivalent to omega naught upon 2 pi. So it means that we can replace this 1 upon t naught with omega naught upon 2 pi. So that's all I've done here. I've got 1 upon 2 pi and we've put up the omega naught here. But now we know that the period is going to tend off to infinity. So as that period tends off to infinity, we know that the number of components tends off towards infinity. So it means that this discrete n omega naught will tend towards a continuous variable omega. So we can replace this n omega naught with our d omega. And we know that the values of Cn will tend towards a continuous function f of I omega, and we can see that our summation then will tend towards an integral, and also the limits again can be extended to minus infinity to plus infinity. So now if we incorporate all of this into this equation here, then we're going to end up with f of t equals 1 upon 2 pi times the integral from minus infinity to infinity of f of I omega e to the I omega t by d omega. And this is our inverse transform. So let's interpret what we've done so far in the derivation of the forward and inverse transforms in terms of inner products. Now we've written out the forward transform here, so we're going from a time domain into a frequency domain. And we've seen that whenever we've done the derivation of that, that's going to be equivalent to saying we've got a vector A, which is f of t, and we're trying to find the components of that vector. Now, in order to find the components of the vector, which the components are given by an, we take the dot product of that vector with the orthonormal basis e hat n. Now that's equivalent to what we've got up here. Our values of an, which are as our constant coefficients of this vector A, is equivalent to our f of I omega. The vector A is equivalent to our function f of t, and the orthonormal basis e hat n is equivalent to our e to the minus I omega t by dt, and the dot product is equivalent to multiplying both these together and integrating from minus infinity to infinity by dt. And if we do that, we're able to find our values of an. Now equivalently, the inverse transform, we're going from the frequency domain back to the time domain, and that's equivalent to saying we want to work out the full vector A. In order to work out the full vector A, we take the values of an, which is our coefficients, and we dot them with the orthonormal basis e hat n. So this here, e to the I omega t, is our e hat n, our an is our value f of I omega, and our vector A is a function f of t. And one other thing to note here is we've got the 1 upon 2 pi, which occurred because we needed to normalise the vector space. Now one other thing to note here is that we've got this term here en hat and en hat. So both of these are the same in this little simple case, but they're not the same here in this forward and inverse transforms. In the forward transform it's e to the minus I omega t, and in the inverse transform it's e to the I omega t. Now you can see why this is going to occur, and we'll talk about it down the next slide as well. But if we were to look at the dot product of two real vectors, so vectors are going with real components, so it would be a dot b would be the sum from n equals 1 to some value of I of an times bn. So that's assuming that it's a purely real values of a and b. But if the values for a and b aren't purely real, if they've got complex terms, then the dot product is going to be given by the sum from n equals 1 to infinity of an and the complement bn. Okay, so this complement here, this factor of the complement here, is, and the difference between this and this one here is really the difference here what we see from this minus sign and the plus sign on this. So again, we'll look at that again in the next slide. Now we note that we're only working out the Fourier transform of real valued functions of time, so we don't have a function of time that's got an imaginary part to it. So that means that whenever we're in the frequency domain and we're going back to the time domain, it means that all of the imaginary terms must disappear. So how do we make them disappear? Well, we make them disappear by making sure that they're complex conjugates. So the plus I will always disappear, it will always cancel out with the minus I. So back in the time domain we'll have a purely real function, and we do that by ensuring that our orthonormal basis are conjugates. that is e to the I omega t and e to the minus I omega t are conjugates, and we're going to be looking at in another video when we look at Hermitian symmetry, and we're going to look at that and also the eigenvalues, eigenvectors, and how we can relate this all that to the idea of the Fourier transform, but that's for another video. So just to finish up, we've worked through quite a lot in this video here. We've worked through a graphical derivation and also a mathematical derivation of the Fourier transform, and we're left with a transform pairs. So our forward transform here, going from the time to the frequencies given by f of I omega equals the integral from minus infinity to infinity of f of t e to the minus I omega t by dt. And our inverse transform, going from the frequency domain back to the time domain, is given by 1 upon 2 pi the integral from minus infinity to infinity of f of I omega e to the I omega t by d omega. So that's all there is for this video. Thank you for watching, and I'll get you in the next video. Goodbye.